Chapter 3, Section 1 is a review of the concept of moles and molar mass, how to convert from grams to moles and moles to grams. And what we need to do that conversion is the formula mass. So sometimes you see this called the molecular mass, but ionic compounds are not molecules, so it might be easier to call it the formula mass. And that is the mass of a formula unit. A good example is down here, because sodium chloride is not a molecule, we can't call this the molecular mass, but 1 unit of sodium chloride has 1 sodium and 1 chlorine, and if you add up those average atomic masses that you find for sodium and chlorine on the periodic table, which is 22.99 AMU for sodium and 35.45 AMU for chlorine, you get the 58.44 AMU of a unit of sodium chloride. If you have a mole of sodium chloride, a mole being Avogadro's number, this amazingly huge number, 6.022 times 10 to the 23rd. If you have that many sodium chloride units, you have a mole of sodium chloride, and that would be 58.44 grams. So that gives you an idea of how small an AMU, atomic mass unit, is, that you need this many of them to get a gram. But it's a very convenient number because we can use it to talk about grams, which are measurable, instead of trying to talk about AMUs, which are vanishingly small, very difficult to see. And so this molar mass can be used as a relationship to convert between grams and moles, which is something that is very, very commonly needed in practical chemistry that you do in the lab. You can measure things in grams, and the reaction that you're doing is based in moles, and so this is a very important thing. We need to do this all the time. This is good to understand and be able to do. This is not something that we have to do very often. We very seldom are concerned with how many individual units of sodium chloride are participating in the reaction. We are usually dealing with moles. But if we did want to convert from moles to any individual unit, it's good to know that Avogadro's number is that relationship. So let's practice calculating some formula mass and some molar masses of these formulas, and then we'll use them in a few practice problems. All right, so for this first molecule, this is a covalent compound, so we can call this the molecular mass if we want, or the formula mass. We have 3 carbons, so we take 3 times the atomic mass of carbon, which is 12.01. We get 36.03. Then we take 8 times the mass of hydrogen. 8 times 1.008 is 8.064 AMU. 1 oxygen is 1 times 16.00 AMU, which gives 16.00. And then when we add all these up, we have 2 masses that go 2 past the decimal, 1 that goes 3 past the decimal. And so when we get our final sum, we should round it to 2 past the decimal. So the periodic table that I'm using with this class has the average masses just going 2 past the decimal. Some students or professors prefer one that goes 3 places past the decimal. If you have one like that that you'd like to use, that's fine as well. I think for our purposes, 2 past the decimal is okay for much of what we're doing, but that's a preference for you to choose. Let's take a look at magnesium phosphate. We have 3 magnesium, 2 phosphorus, and 8 oxygen that we have to add up. Here's some of the atomic masses I got from the periodic table, and the sums over here that add up to 262.87 AMU, and I am keeping 2 past the decimal still for this formula mass. I just want to take a closer look at this one because some people might be a little bit confused why I am multiplying something with 4 significant digits and ending up with something with 5 significant digits. 8 times 16.00 I'm saying is 128.00 AMU, and I think it's because I think of these formula masses as just adding up all this stuff. And yes, I've added up 8 16.00 values, and so I can still keep a number that goes 2 past the decimal, because each of the things that I'm adding up is going 2 past the decimal. So it's a little bit different than a significant digit multiplication rule. We're just adding up all of these things. Most of the things that we're adding up go 2 places past the decimal, and so our results can all be 2 places past the decimal. So finally, let's do calcium nitrate, which has 1 calcium, 2 nitrogen, and 6 oxygen. So I add up this number of atomic masses, 1 calcium, 2 nitrogen, and 6 oxygen, and the total sum here is 164.10 AMU. So now the molar mass of each compound above is the mass you would have if you had a mole of each of these. 1 mole of this C3H8O molecule would weigh this number of grams. So the molar mass would be that same amount, 60.09, but it would be that many grams. And while some references report this as just grams, I think it's very helpful for most students to always report the molar mass as grams per mole. So then you see that it's not the grams that you have, it's the grams that are in a mole. A lot of people, if they just write this number as 60.09 grams, they get confused and think that's the number of grams in the problem that they have to convert. So I think it's a good habit to put the units for the molar mass as grams per mole. So here is the molar mass for the other 2 substances here. I am using the abbreviation for mole. That's a habit that I have. This is the only abbreviation for mole that is accepted. You can't abbreviate it as just M because that's the abbreviation for meter or for milli, the metric prefix. So you have to use MOL if you want to abbreviate mole. So I've copied these molar masses here next to some practice problems. We're going to use this relationship to convert 0.0360 moles into grams. So we have 0.0360 moles of calcium nitrate. We're going to go ahead and use this conversion factor the way it is, with the grams on top and the moles on the bottom. When I do that multiplication, the moles cancel, and I'm left with grams of calcium nitrate, and it comes out to 5.91 grams of calcium nitrate. For this next problem, we have 45.87 grams of magnesium phosphate, and we want to convert that into moles. We're going to have to put grams on the bottom and moles on top so that we can cancel our grams and end up with moles. And so we divide 45.87 by 262.87, and we end up with 0.1745 moles of magnesium phosphate. This next question is a little bit unusual. We have a number of individual atoms of nitrogen that we want to convert into grams of calcium nitrate. So what we know about the grams of calcium nitrate is its relationship to moles of calcium nitrate. We know that it's 164.10 grams per mole. Another relationship that we can figure out is that a mole of calcium nitrate has 2 moles of nitrogen in it. When we calculated the molar mass, or the formula mass, we used 2 times the mass of nitrogen because there's 2 nitrogen atoms in every unit of calcium nitrate. There's 2 moles of nitrogen in every mole of calcium nitrate. And then a mole of anything, including a mole of nitrogen atom, is 6.022 times 10 to the 23rd, Avogadro's number, of that item. So these are our relationships that we need to use. We're going to be using the last relationship first, because that's the only one that has individual nitrogen atoms in it. So we're going to end up dividing by Avogadro's number. Be careful with the scientific notation. If you are not typing scientific notation into your calculator correctly, you might end up multiplying by 10 to the 23rd instead of dividing by 6.022 times 10 to the 23rd. So if you get a really strange answer, that could be the issue. Our next conversion factor will get rid of moles of nitrogen and start talking about moles of calcium nitrate. Then we can use the molar mass. A mole of calcium nitrate weighs 164.10 grams. And when we do this, when we solve this calculation, we should come out with 4.8 grams of calcium nitrate. So this next problem as well involves individual atoms of things. So I'm going to go ahead and take a little shortcut and replace this nitrogen with oxygen. So 1 mole of oxygen atoms is Avogadro's number of oxygen atoms. Also, with this formula, magnesium phosphate, 1 mole of magnesium phosphate units would have 8 moles of oxygen atoms in them. And then the third relationship we need is the molar mass of magnesium phosphate. Okay, so this mass of magnesium phosphate that we have, 12.87 grams, we would divide that by the 262.87 grams of magnesium phosphate per mole of magnesium phosphate to get moles of magnesium phosphate. And then we would multiply that by the 8 moles of oxygen atom that are in each mole of magnesium phosphate. And then we would multiply that by Avogadro's number, which is the number of oxygen atoms in a mole of oxygen atoms. And we would come out with 2.359 times 10 to the 23rd individual oxygen atoms.